Hi, this is Alex from devstories.eu, Python, Cheminformatics, and AI, episode 14 of 22. Instead of forcing an AI to memorize the absolute potency of every molecule in existence, what if you simply taught it to ask how a molecule differs from its closest known neighbor? This shift in perspective solves a major generalization problem in low data regimes, and it is the core of a framework called Similarity-Quantized Relative Learning, or SQRL. Normally, molecular property prediction treats every molecule as an isolated data point. The model tries to map a structure directly to an absolute property value. With small, noisy datasets, deep learning models struggle to build an accurate global map of chemical space. Previous attempts at pairwise learning tried to fix this by pairing every molecule with every other molecule in the training set. That approach floods the data with comparisons between completely unrelated structures, drowning out the useful local signal. SQRL fixes this by restricting the training data to pairs of molecules that are structurally highly similar. The model learns to predict the relative difference in their properties, known as delta Y. This is achieved through a specific dataset matching step. You do not feed the model individual molecules, you feed it pairs, but only if they pass a strict similarity threshold. Let us walk through the logic. You start with your standard training set of molecules and their known potencies. First, you calculate the pairwise distances between all molecules using a metric like Tanimoto distance on Morgan fingerprints. Here's the key insight. You set a distance threshold, alpha. Let us use a Tanimoto distance threshold of 0.7. You iterate through all possible molecule pairs. If the distance between molecule A and molecule B is 0.7 or higher, you discard the pair entirely. If the distance is strictly less than 0.7, you add this pair to your new relative training set. The target variable for this new pair is no longer an absolute potency. It is the exact numerical difference in potency between molecule A and molecule B. Now you train your neural network. The network generates a mathematical representation for molecule A and a representation for molecule B. It subtracts the representation of B from the representation of A. That resulting difference vector is passed through a final layer to predict the delta Y. By filtering out the noise of dissimilar pairs, the network is forced to focus exclusively on local, high-signal chemical changes. It learns exactly how a specific structural tweak alters the activity. This makes the model highly sensitive to activity cliffs. That covers training, but what about predicting a brand new molecule? When a new structure comes in, the system scans the original training data to find the single closest structural neighbor based on that same Tanimoto distance metric. The network evaluates the new molecule against this nearest neighbor and predicts the relative delta. Finally, you take the neighbor's known absolute potency, add the predicted delta, and you have your final prediction. By restricting the training space to highly similar pairs, you stop asking the model to learn the entire chemical universe and instead train it to become an expert in local chemical gradients. That's all for this one. Thanks for listening and keep building.